We've been looking at example Shplait continuations, but since we're implementing a Mo interpreter, let's look at continuations in Mo terms. So here I have a continuation 3 plus dot. That is, we already have the value 3 for the left-hand side of the plus. We're waiting for a Mo value on the right-hand side of the plus, and then we'll actually add them together. To represent these continuations in our Mo interpreter, I need a new data type, which I'll call continuation, and we'll have different variants to represent different kinds of to-do list entries. One of them is just like the one illustrated here, a plus continuation. In that case, when the dot is on the right side like this, that means we've already interpreted the left-hand side. So that means we already have a value over there. So that's why my do plus k variant of the continuation type has just a value inside of it. This is not quite right, but this is a step to get to the right place. So the name of the continuation do plus k means how should you continue? You should actually do the plus once you get a value back for that right-hand side. So concretely, we would write 3 plus dot, we would write that as do plus k int b3, meaning once you actually get another value back, actually add it to 3. What if the dot is on the left-hand side? That means we're working to get a value here. We don't have a value yet for the right-hand side, though, because we do that after the left-hand side. So in this case, we have an expression instead of a value on the right-hand side. So instead of a do plus k, which can't represent this, we will have another variant of our continuation that we'll call plus second k. So this means you need to do a plus. That's how you continue. But even before you can add, you have to evaluate the second expression, the one that's on the right. And in that case, we have an expression instead of a value. And of course, anytime we keep an expression, we also need to keep the environment that goes with it. So we have these different kinds of plus continuations. One where we're working on the left, and we need to remember to go work on the right and then do the addition. And one where we've already done the work for the left, and we just need to finish up by performing the plus. So this example here would be an app-e f of 0 for that right-hand side in the empty environment, say. Now, the reason I said before it's not quite right, these are variants that I've been writing down, it's because my continuation is actually a sequence of these things, right? It's a stack or a list of these kinds of things to do. We could use this definition of continuation and say these are actually continuation frames, but instead I'm going to build the list structure into the continuation type. So every time we have a continuation, once you do some next step, but then there's always more to do. Well, not always more to do. Sometimes you really are done, and so we need another variant of our continuation that is called done k that does not have a continuation that it chains to. So this is an empty stack, if you will, or it's our starting continuation. When you start out evaluating a program, you don't have anything else to do, but the continuation grows and shrinks as you run the program. So now we can represent this example here, which says there's a plus nested inside of a plus. We would represent that as a plus second k, because that's what we need to do next. That's the way to continue, is to start working on the right-hand side and then eventually add. Once we get a value for that, then the next continuation here is a do plus k, right? So plus second k has the expression we need to evaluate and the things we need to do after we finish the plus, which in this case is another plus. Once we finish this plus, though, that's the end of our to-do list, and so that's why it ends with done k. So this is the correct new variants that we need to add to continuations, at least for dealing with addition, but we have various other forms to consider as well.